Thank you. So the secretary recommendation problem is a joint work with Martin Hoefer from Goethe University in Frankfurt and Rann Smorodinsky from the Technion in Haifa. Quick overview over the contents of the talk. At first, I'm going to introduce the model. Then I will motivate and give you our benchmark case, which will then be used for our results. All of us know the secretary problem, I think, but just to repeat it quickly, there are n candidates that apply for a position as a secretary, and you have to decide on the spot after seeing a single secretary whether you want to hire him or take the consider the next applicant. So whenever you see a person, you get to see what their value is, and then you have to decide whether you want them or not. This was solved optimally back in the 60s, where the decision maker just takes the first n over e candidates into account and never takes them, and then takes the first person that is better than the previous ones. So in this example, the green one would be rejected outright, the red one also, and then the blue one, having the highest utility of the candidates, would then be taken. And the fourth candidate would never be observed by this algorithm. We augment this by splitting the decision maker into two. We have now a sender and a receiver, and the sender is the one that observes the candidates, and the receiver is the one making the decision, which affects both players. So this means a candidate has two values, one for the sender and one for the receiver. We assume that those values are non-negative. The candidates arrive one by one in uniform random order, just in the original secretary problem. And in each round, the sender observes a candidate and then sends a signal to the receiver. And the receiver then hires or rejects the candidate. The main question here is, how can the sender exploit knowing more than the receiver? And as always in online problems, how much does the sender have to lose because the candidates arrive online? What we are doing in the paper is we are designing good algorithms and compare them to a benchmark and show that the algorithms achieve good approximation factors compared to this benchmark. In the study of Bayesian persuasion, which is the game between the sender and the receiver, we assume that the sender has commitment power. This means that the sender commits to a signaling mechanism and communicates this mechanism to the receiver and is not allowed to deviate from this mechanism in any way. So in each round, the mechanism then takes the set of known candidates and produces the signal. And all our mechanisms we consider are direct, meaning that the signals are either hire this candidate or don't hire this candidate, which is also a standard result of Bayesian persuasion, and persuasive, meaning that it's in the receiver's interest to follow the recommendations given by the sender. Just quickly, the formal setup of our problem. We have a candidate set of 1 through n. Each candidate has two values, one value for the receiver and one value for the sender. The values are determined in advance, but neither the sender nor the receiver are aware of these values. Then the candidates arrive online in uniform random order, and upon arrival, they show themselves to the sender, and the sender observes the value of the candidate. Then, according to her scheme, the sender signals yes or no, and the receiver then makes an irrevocable decision. Whenever the receiver hires the candidate, the game is over and the utilities are realized. And if the receiver rejects the candidate, the next candidate arrives and is observed by the sender. Now, this leads us to the question what a suitable benchmark might be. One could think that as we are trying to optimize the sender utility, it would be good to compare it to the best candidate for the sender. But unfortunately, this isn't a very good benchmark, as we can see through this observation. Whenever the receiver does not take into account what the sender tells him, he can just take a random candidate and receive an expected utility of mu, which is the expected utility of a random candidate. So this means that whenever the sender wants to be persuasive, she has to guarantee that the receiver will get at least a utility of mu. And in this example, where there's only a single valuable candidate for the sender, and all other candidates are valuable for the receiver only, you can see that whenever the sender guarantees a utility of mu to the receiver, the sender herself can only get 1 over n. So if we use this as our benchmark, there will be cases in which no constant approximation is possible. So in order to remedy this, we use a different approach and assume for our benchmark case that the value pairs of all candidates are known to both players before the game starts. So the advantage the sender now has over the receiver is that the sender knows the current candidate, but the receiver doesn't. So in this example here, we have a set of candidates where the horizontal axis is the receiver value and the sender axis is the vertical axis. Any mechanism will yield an expected utility somewhere in the convex hull of these candidates. As we've seen before, the receiver utility should be above the line going through mu. On the other hand, everything is bounded from above by the Pareto frontier. So we have the following. Any persuasive mechanism should be inside the screen area. Now, the best utility the sender can achieve inside the screen area is right at the intersection of the line going through mu and the Pareto frontier. The question is then, is this also the optimal achievable utility, or is it not possible to get this for the sender? And our first small result is that yes, this is achievable by the so-called Pareto mechanism. This mechanism identifies the two candidates A and B that are on the line segment that goes through the receiver coordinate at mu, and then by setting probabilities just right so that the expected utility for the receiver is exactly mu and only signaling for one of these two candidates, A and B, the sender can achieve the utility at the black square. Now here it says also if A does not exist, set C equal to B. What does this mean? It could be that B is the best has the best utility for the sender. So that B could be somewhere around here. Then the Pareto frontier would look a little bit different, would look like this, maybe. And there wouldn't be any A. So then obviously only recommending the candidate B would be Pareto dominant over recommending the utility, the expected candidate here, as it's better for the receiver and it's just as good for the sender. Right, so now we've seen the benchmark and know that the Plex square is possible. Now back to our secretary assumption, which is that neither the sender nor the receiver know the candidate's values in advance. Now this leads us to another problem, because the receiver wants to know whether he should deviate or follow the recommendations given by the sender. But if the receiver does not know anything, how can he then calculate whether he wants to deviate? So our approach is the following. We say that persuasiveness for the receiver should hold even if the receiver knew all the candidate's values. So then he can calculate what the expected utility would be and then calculate whether he would want to follow the recommendations or deviate from them. Now this leads us to the question of how much expected utility the sender can achieve under these assumptions, namely that the sender does not know the candidate's values and that persuasiveness shall hold even if the receiver knew all the candidate's values. This gives our first main result of the paper. For any set of candidates with non-negative values, the growing Pareto mechanism, which I will be defining on the next slide, is persuasive, and it also achieves an expected utility of at least 1/3 square root of 3 of the expected utility in the benchmark scenario, where again, in the benchmark scenario, both players know all values, and here in the secretary scenario, the utility of the candidates are unknown. So why is it called the growing Pareto mechanism? Well, it works the following way. At first, it samples a few candidates to get a feeling for the candidate values and signals no in every round. And then with the growing set of candidates, it employs the original Pareto mechanism in every round and signals higher if the current candidate is the one that is recommended by the Pareto mechanism for this subset of candidates, and it signals no in the other cases. Now I'll give you a short example of this. So let's assume that those are the candidates as they were sampled during the sample phase. Now, if a new candidate arrives, we have to run the Pareto mechanism and see whether this new candidate will be recommended. Obviously, in this case, it's inside the convex hull of the candidates, so it will not be recommended. If another candidate arrives, the same thing happens again, and we see that this candidate will not be recommended either. But as this is an example, there's always a guy that's being recommended. So in this case, we can see that the Pareto frontier goes through the new candidate and it's the best candidate for both players. So it will be recommended. Here I'll give you an overview over some of the results for a cardinal receiver. Cardinal meaning that the player would want to maximize the expected utility gotten from the hired candidate. In contrast to this, we also considered the ordinal objectives, which means that we maximize the probability of only getting the very best candidate. Additionally, we have a difference between disclosure and non-disclosure, meaning that candidates that are rejected by the receiver are either disclosed or non-disclosed, meaning the receiver will learn their values and might use this information in future rounds or will not learn. What we've just seen with the growing Pareto mechanism was the 1/3 square root of 3 here, where the sender also follows the cardinal objective. Additionally, if the sender follows the ordinal objective in the secretary scenario without disclosure, we get a little bit better result of 1/4. Very interestingly, though, on the other hand, if candidates are disclosed to the receiver and the assumption is that neither sender nor receiver know the value, so we are in the secretary case, then we can only get a utility of theta of 1/n for the sender in both cases of ordinal or cardinal objective for the sender. And this is very interesting because the easy algorithm of just recommending a random candidate already gives us a utility of 1/n in any case. So basically what this says is that nothing can be done for this scenario. To complete the picture, we also considered the ordinal receiver, where the receiver only is interested in hiring his best candidate. And here we can see that we achieve tight bounds in every case and that we get a constant approximation ratio for every candidate, for every scenario. Where in the benchmark scenario with known utilities, the sender basically gets her best candidate every time, regardless of disclosure of the candidates. And in the secretary scenario, we get the 1/e, which is the bound from the original secretary problem without disclosure. And with disclosure, this goes down a little bit to 1/4. Thank you.